Hey, what's up? I just wanted to make this video because lately I've been listening to the all the Mark Sargent podcasts, radio, the Strange World radio programs, and everything. Where, as I'm sure a lot of you know, he's been interviewing the different professional guys. The Navy guy. First it was the Navy Sea Sparrow instructor, and then the retired submarine guy. And then there was the surveyor, and the last one was the flight instructor guy. And if you haven't checked these out yet, I would totally recommend them because they've just been incredible. But yeah, one of the things that they keep talking about in all these interviews is the use of the gyros on the ships and the planes and the submarines using gyroscopic navigation. And this is something that I wasn't really familiar with before, so I just found it to be incredibly fascinating. Yeah, basically just found it to be a very intriguing topic overall, and I've kind of been obsessed with learning about just gyroscopes in general, and gyroscopic navigation, and gyroscopic precession, and rigidity in space, and all these different associated concepts and how they work. And so at this point, I'm still in the process of looking into it, and more or less I just wanted to make this video as a way of maybe just encouraging as many people as possible to start looking into this more, and maybe they can find some people to interview who are experts in this whole field. Not that the guys who've been interviewed already aren't pretty knowledgeable about how these things work, since they use them all the time. But what's been interesting to me is just exploring this idea of, because everyone that's been interviewed so far, they talk about how the whole way that the gyroscope works is that when it's spun up and it's spinning at such a high RPM, the whole idea is that it isn't affected by gravity, and it just that's the whole concept of rigidity in space, is that it maintains that X, Y, and Z axis perfectly. And so of course this would mess you all up if you were actually on a globe, and it would really only work on a flat plane model if everything was at the same reference point of X, Y, and Z, like on a 3D grid. So it's interesting because they're saying it doesn't ever compensate for gravity, or doesn't ever, the whole idea of a gyroscope is that it resists gravity. And I mean, you can go online and look into all these different ways in which this is, it's pretty easy to see how gyroscopes, they basically defy gravity, and there's actually a lot of experiments and anti-gravity, devices and different types of experimentation, just using these principles. Actually, even like sort of simple flying saucers that are all based on gyros and everything. So it's interesting because I'm looking around and I'm trying to find more information on this. And one thing I came across was this 1960s training film from the Navy, and it's amazing because in this first part here they talk about how, just like the guys were saying, that the gyroscope on its own will totally maintain the same X, Y, and Z axis, independent of a ball Earth, where up and down is going to, your Y axis is going to change depending on when you move around the ball, and so that's like a problem.
Modern high-performance aircraft require electric gyroscopic instruments. The turn and slip indicator, the attitude indicator, and the directional gyro. These electric instruments are dependable at extremely low pressures and temperatures, where gyro suction instruments are unreliable. This film will explain the theory of operation of some of the newer electric gyroscopic instruments. To understand any gyroscopic instrument, you must understand the principle of the gyroscope. It consists of a rotor mounted in a gimbal. The rotor can spin in one plane only. When another gimbal is added, a second plane of movement is possible. And when this assembly is mounted in bearings, the rotor has three planes of movement and can assume any possible attitude. This is now a freely mounted gyroscope. A spinning gyro has two important properties: precession and rigidity in space. All of its practical applications are based on these two properties. As for rigidity in space, the spinning rotor remains in its original attitude, while the gimbals and base move around it. In other words, the gyro maintains its axis in relation to space and not to the surface of the Earth. If a gyro moves around the Earth, its axis is vertical to the Earth's surface here, at an angle here, and horizontal here. The gyro will resist any force that attempts to change its plane of rotation. This leads to the principle of precession. When a downward force is applied here, the gyro moves, but not in the direction of the applied force. Instead, it moves at right angles to the applied force. This action is known as precession. If an upward force is applied at the same place, the gyro again precesses at right angles, but in the opposite direction. The explanation is simple. The rotor is spinning in this direction. When the force is applied, the gyro precesses in the direction to align the direction of rotation with the direction of the applied force. The rate of precession is in direct proportion to the applied force. Small force, slow precession. Greater force, faster precession. If enough force is applied, the gyro precesses a full 90 degrees. However, at or near 90 degrees, it will tumble and go out of control. This disadvantage must be overcome in gyro instruments. Another disadvantage comes from the gyro's tendency to drift away from its original attitude. There are two types of drift. One is mechanical, due to friction in the bearings. This is actually a form of precession. The other type, known as apparent drift, relates to rigidity in space. Once again, consider this condition. The gyro maintains its attitude while the Earth turns under it. Every 6 hours, the gyro drifts through 90 degrees in relation to the Earth's surface. In order for the gyro instrument to be dependable, drift must be corrected continuously. There are several types of erection systems that correct for drift. The principle back of all these systems is based on three steps. The direction and degree of drift are measured by electrical or mechanical sensing elements. These elements then control the application of a proper force to the gyro, and it precesses back to its normal attitude. All gyros in this film are actually the rotors of electric motors. However, for simplicity, we will represent them like this, this, and this. The MA1 compass system combines these two instruments into one system that uses their advantages and eliminates their disadvantages. The magnetic compass, in the form of a flux valve, is mounted remotely in the tail or wingtip, away from the worst magnetic disturbances within the aircraft. The gyro is also mounted remotely from the indicator dial. The system is designed for two modes of operation. In the free gyro mode, the gyro alone controls the indicator dial. In the slaved mode, the magnetic compass controls the gyro. We will first examine the slaved mode of operation. We will represent the flux valve as a magnetic needle mounted on the rotor of a synchro transmitter. The needle will remain aligned with the Earth's magnetic field while the aircraft turns in any direction. The stator of the compass transmitter is connected electrically to the stator of a synchro control transformer. The gyro's outer gimbal is mounted on the rotor of this synchro. When the outer gimbal is properly oriented to the magnetic needle, there is...
And then when you get into this other part, it goes on and explains how. So it's a two-part system where it has to constantly be adjusting for the curvature and for the the magnetic. So the second part uses supposedly a magnetic compass that is constantly causing the gyroscope to readjust itself to magnetic north and reorient itself, and then the gyroscope holds it in place until it gets out of sync, and then it has to reorient, which to me just seems like kind of a very contradictory idea altogether. The fact that the gyroscope, the whole purpose of the gyroscope is to maintain that rigidity in space, and then supposedly you're using the magnetic compass to constantly reorient the gyroscope, which is independent of gravity and independent of magnetism, right? And the Navy guys and the flight guys, they all say that of course the gyroscope doesn't do this. So it's interesting because this is from 1960s, and obviously the system that it's describing is going to be vastly simplistic compared to whatever they're using now. I mean, they talk about using gyros that have, they use lasers and things like this, so they're insanely precise, and I'm assuming vastly more powerful, so that the variance is going to be minimal, if not non-existent. So to me, this is the real issue that has to be, is this just propaganda, this whole idea that they show the globe Earth in this video, so it's kind of funny if it is just a piece of propaganda to explain away this very thing, like how gyroscopes could work on a ball Earth, because from everything we're looking at, it totally flies in the face of it. So if gyroscopes are indeed a proof of the flat Earth, as it seems like they are, then this is the discrepancy that needs to be, I think, really fleshed out, because this could be total bunk, because none of the guys who are using the systems talk about a magnetic compass that is constantly correcting and readjusting the gyro. So what I'm curious about is like whether that's really true, and does the gyro just operate independently the entire time of a sea voyage or a flight, or does it constantly have to sync up with a magnetic compass and readjust? I mean, so that's the question of whether it really does go back and forth between adjusting to a magnetic compass, or whether it's just completely independent the whole time. Because that makes all the difference in the world. So I think we need to do a lot more investigation into this and really get to the bottom of it. But it's a pretty fascinating topic overall. So hopefully some more people can help shine some insight into this. Interviews is the use of the gyros on the ships and the planes and the submarines, using gyroscopic navigation, and this is something that I wasn't really familiar with before, so I just found it to be incredibly fascinating. Yeah, I basically just found it to be a very intriguing. Retired submarine guy, And then there was the surveyor, and the last one was the flight instructor guy. And if you haven't checked these out yet, I would totally recommend them because they've just been incredible. But yeah, one of the things that they keep talking about in all these podcasts or radio, the Strange World radio programs and everything, where, as I'm sure a lot of you know, he's been interviewing the different professional guys. The Navy guy, first it was the Navy Sea Sparrow instructor, and then the submarine. Hey, what's up? I just wanted to make this video because lately I've been listening to the all the Mark Sargent topic overall, and I've kind of been obsessed with learning about just gyroscopes in general, and gyroscopic navigation, and gyroscopic precession, and rigidity in space, and all these different associated concepts and how they work. And so at this point, I'm still